approach for early outbreak detection of emerging diseases based on some product networks. So first of all, outbreak detection can be seen from the perspective of syndromic surveillance, in which we monitor health data in order to detect outbreaks of infectious diseases early on. This is important to apply control measures which can prevent the further spread of the disease. Throughout the slides, I will use an example where we monitor emergency department data. So basically we can see a timeline where patients arrive at the emergency department over time. And to make things a little bit easier, we group these patients together according to pre-specified time slots. So we have sets of patients over time, and each set of patients can be annotated with some kind of environmental information. For example, this could be as a weekday, assuming during the week we have a different distribution of patients, for example, than during the weekend. The common approach to syndromic surveillance is to first decide on a disease, and based on the disease, we define a disease pattern which is monitored over time. For example, if we want to monitor influenza cases, we could create a disease pattern which contains the disease pattern fever. And basically what we are then doing, we only take a look at a part of the patients which have the particular disease pattern, count them, and that information can be then put into such kind of time series on which we can apply statistical algorithms in order to detect any kind of change, in particular an increase of infections, as it can be seen here in the last part of the time series, which might indicate an outbreak of an infectious disease. However, this approach is a very handcrafted approach because it requires to generate some kind of disease patterns by experts. And moreover, we can only monitor diseases which are known beforehand. To overcome this problem, we see the problem of syndromic surveillance more from a general viewpoint, where we want to monitor the full set of data to detect any kind of outbreak. As it can be seen here, so instead of picking single patients from the sets, we now take all the patients and put it in our model, which then can detect outbreaks. And our approach is based on some product networks. And the general idea is to monitor all possible kinds of disease patterns at the same time. However, this set of disease patterns can be quite large. Therefore, we reduce the complexity by only considering disease patterns with a specific number of conditions. So we will denote that throughout the slide with Sn, where n is the number of conditions in the disease pattern. Based on these disease patterns, we then extract all the time series from the data for the disease pattern. So we have a set of time series. These time series do we join with the environmental variables, here denoted as E. And on this data set, we learn SPN, which models the interaction or the correlations between the disease patterns and the environmental attributes. Here on the right of the slide, you can see an exemplary SPN, which has been learned over 3 attributes. 2 of them are syndromes, which could be fever and cough, and the other one is an environmental variable, which represents the season. So in general, some product network consists out of product nodes and subnodes and leaf nodes. In the leaf nodes, we have univariate distributions over single random variables. For the product nodes, we combine multiple univariate distributions, or actually also a bigger set of an SPN. We combine them, and actually product nodes represent independence among these underlying distributions. In contrast, some nodes represent a mixture of distributions among the same random variables. So if we read this SPN from top to bottom, we can see that the first node is a product node, which splits the distribution of CAF cases from the other data, the other random variables, which basically means that the distribution of CAF cases, which we learned from the data, is independent of the other two attributes. In contrast, in the lower part of the SPN, we can see that we have two clusters which are separated by a sum node. One cluster only containing cases in the winter and one cluster only containing cases in the summer. And we can see that during the winter, we have a different distribution of fever cases than during the summer. So basically, this SPN, which can be seen here, can track the correlations that we have different distributions of fever cases in the winter and in the summer. Usually, these SPNs are quite or much bigger. This is only an example. One advantage of SPNs is that we also can adapt the structure of the SPN to represent the conditional joint probability distribution. For example, we can condition the SPN on the environmental information, which is season equals summer. What we do in this case is we forward this evidence to the leaf nodes, to the respective leaf nodes, so in this case season. We evaluate the probability and propagate it bottom up in the SPN, and every time we reach a sum node, we update the weights at the sum node. In the last step, we remove all the leaves which are responsible for the random variable season, and then we would result in such kind of SPN, which we then can use to query. So what we can see here is that now the right cluster, which initially represented the summer, has now a weight of 100%, while the cluster for winter has a weight of 0%. So in order to detect outbreaks with this SPN, so we have learned the SPN to represent the normal behavior in the data. And in order to detect outbreaks, we evaluate or propose a novel extension to SPNs to properly reason with p-values. So normally in SPNs, we only evaluate normal probabilities or densities. However, we propose to use p-values, which require a specific way to combine them so that can maintain their meaning. So instead of multiplying in product nodes, we have considered to use methods with which independent p-values can be combined. These are, for example, the Fisher's or the Stouffer's method. And for some nodes in the literature, it's proposed to use either the harmonic, the geometric, or the arithmetic weighted mean. So an evaluation basically consists of 3 steps. So we observe a new set of patients and some kind of environmental variables. So first we condition on the environmental variables. Then we compute for each disease pattern, which is included in our SPN, one particular p-value. And then in the final step, we aggregate all the p-values by taking the minimum p-value, which is the most obvious anomaly in the data. So here we can see an example. For example, we observed in the new set of patients 7 CAF cases. So we evaluate, or given this evidence, we move it forward to the leaf nodes, which represent the CAF cases, evaluate a p-value, and then propagate it up using the respective methods to join them. This can also be done for the fever cases. So here in this case, we have, for example, 4 fever cases. So we compute in both leaves here a p-value, which is then merged at the sum node. In our work, we also propose a way how we can also approximate the p-value of higher order syndromes. So initially, we only have built our SPNs on the syndrome fever and cough, but we still can evaluate some kind of p-value that fever and cough appears together. This can be done by just evaluating both conditions at the same time. For evaluation, our evaluation is based on synthetic and real data. For the synthetic data, we have used a common data set used in previous works before. It's a fairly simple data sets where we have for S1 approximately 24 disease patterns and for S2 270 disease patterns. In addition to the synthetic data, we have evaluated on real data, which is data from a German emergency department, in which we injected synthetic outbreaks. This data set is, compared to the synthetic data set, approximately twice as complex. To measure the performance of our approaches, we use AIME curves. AIME curves are similar to ROC curves, but instead of having the true positive rate on the y-axis, we have the detection delay. The detection delay is the amount of time needed till the outbreak could be detected by the algorithm. And to further only focus on lower false alarm rate, which is very important in syndromic surveillance, we only evaluate the partial area under this AIME curve. Note that smaller values represent better results. So these are our results. We have evaluated two scenarios on each data set, one for only monitoring disease patterns of S1 and one for disease pattern S2. We have compared to some baselines, which we have proposed in an earlier work, which already perform quite good. Then we have compared to some kind of common anomaly detectors and to a state-of-the-art algorithm, which is a WSRE algorithm, which is a state-of-the-art algorithm in the area of non-specific syndromic surveillance. And as you can see here in the results, we could improve over the state-of-the-art algorithms. And in particular, we could do that on both data sets. Further information why the baselines here work so good can be found in another work of us. Taking a closer look at the last line where we have monitored the syndromes of length 2 or less, we also have plotted the AIME curve for this to see the difference. As I said before, for our evaluation before, we only evaluated the partial area for a low false alarm rate. And in this curve, we can also see that our approach is better also for higher false alarm rates. So to sum it up, in this work, we have proposed an approach for the monitoring of multiple syndromes at the same time in one model. And in particular, in this model, we also include some kind of environmental information which can help to adapt to the certain circumstances when we evaluate the syndromes. Therefore, we propose a novel approach to reason with p-values in SPN in order to detect anomalies. And in our experimental evaluation, we could show that our approach, which is based on computing of p-values in SPNs, could improve over state-of-the-art algorithms in the area of non-specific syndromic surveillance. That's it. Thank you.